Welcome back to trigonometry. Today we're going to be looking at the trig functions, specifically how to graph them and then what some of the characteristics of them might be. We're going to get into sine and cosine functions with this recording, and then future recordings we'll get into the tangent and all the reciprocals as well, like the cotangent, cosecant, and secant. But we're going to look at each function, look at how to graph, and then look at things like domain and range, what kind of function it is, etc. Okay, so for those of you who are more artsy and like to draw things, this might be up your alley. I don't know. Alright, so let's get started. Let's start out with the sine function. Okay. You guys have learned about functions in the past, like in college algebra and such. You know, a function is a relation where each input has one output. So, like if you have y equals sine x, each value you input for x, you're going to get one output for y, so you get ordered pairs. And then you can plot the ordered pairs and connect the dots. You've got this nice little graph. And functions will pass the vertical line test. You sweep a vertical line across the graph. It's only going to cross one point at a time. So since this is a function, we could also write the equation f of x equals sine x. F of x is a fancy function notation, can replace y. Okay, so we're going to dive right into graphing this. Now let's think for a second about what we've already learned about sine. If we go to our unit circle, on the unit circle, okay, just bear with me here, we're going to be flopping back and forth with x, y values. On the unit circle, the y values give us our various values for sine. And at 0 degrees or 0 radians, sine value starts with 0. And as you increase your angle measures by degrees or radians, the sine gets the sine values, the outputs, like sine of 30 is 1/2, sine of 45 degrees is square root of 2 over 2. As you input each of these angle measures, the outputs for the sine keep climbing and climbing and climbing to get to 1 when you hit pi over 2 or 90 degrees. And then they start decreasing down to 0 as you go towards pi or 180. And then they keep decreasing down to -1 as you go from pi to 3 pi over 2. And then they start increasing up to 0 again when you hit back to 0. And even though the circle only shows 0 to 360, you can keep going around for higher angles. Like, you know, you go around again, you can get up to 720 degrees. You go around, you know, or you can go the other direction to get negatives and so forth. So, but what's happening here, as shown pretty clearly by a circle, is that the values, the inputs keep getting higher or lower depending on what direction you're going, but the outputs keep circling back and starting over. Where they were here, they have this nice cycle, and then it comes back to here. And it keeps cycling like that. So the sine function, having these outputs that are, you know, consistently cycling this way, makes the sine function be something called a periodic function. If you think about a period is something that occurs very regularly. Like in high school, you know, you have first period, second period, third period for your classes. Well, you have this regular schedule, and you cycle through those classes every day, and then next day you start the cycle, you start it all over again. Period 1, period 2, period 3, you know, all the way to period 7. Or even if you're on block schedule, it might be every 2 days you start your schedule over or something. But it's very consistent and very regular and just keeps repeating itself over and over again, the same kind of pattern. And that's what happens with sine functions. So they are periodic. They repeat themselves every 2 pi, whether you're going in the positive direction or in the negative direction. This happens. Okay, so let's use some of our knowledge about that to help us to get a good graph for the sine. For graphing the sine, the x values are going to be the angles that we input. The y values are going to be the outputs from that. So like let's say you put in 0 for x. Sine of 0 equals 0. So y is 0. Let's say you put in, think about your unit circle, how that works. Like say you put in pi over 6. Sine of pi over 6 is going to give you 1/2. Say you put in pi over 3. Sine of pi over 3 is going to give you square root of 3 over 2. You get some interesting results here. If you put in pi over 6, you get 1/2. You can put in pi over 3. You can put in pi over 2. You can put in 2 pi over 3. You can put in all these different values. 5 pi over 6. Pi. 7 pi over 6. 4 pi over 3. 3 pi over 2. These are going to be all of our inputs. I'm just pulling these from the unit circle to make things a little easier, but you can pull others. You don't have to pull these. You don't necessarily have to pull this many either. For now, I just want to demonstrate the concept of the graphing, but but you know, if pi over 6 is 1/2, and then we learned about how pi over 3 is square root of 3 over 2. But honestly, when you go to graph it, it's going to help to have a decimal approximation. Because how the heck do you figure out where square root of 3 over 2 is going to be? It's around 0.87, roughly. Okay, then we know pi over 2 is sine of pi over 2 is 1. Then sine of 2 pi over 3 is square root of 3 over 2, or about 0.87. Sine of 5 pi over 6 is 1/2. Sine of pi is 0. And then we go negative. See? We had positive climbing up, then positive going down, and now we have negative as we go down. Negatives. So sine of 7 pi over 6 is negative 1/2. Sine of 4 pi over 3 is the negative square root of 3 over 2, or negative 0.87. Sine of 3 pi over 2 is negative 1. Sine of 5 pi over 3 is again negative square root of 3 over 2, or about negative 0.87. Sine of 11 pi over 6 is negative 1/2 again. And sine of 2 pi is 0. And then at 2 pi, we're back here, it starts all over again. Climb higher, and then this pattern is going to repeat itself over and over again. You're going to go from 0 to 1/2, up to 1, back down to 0, up down to negative 1, back up to 0, and so forth. So let's go ahead and plot these values here on a grid. Let's see, let's mark out the grid, and let's see what this curve is going to look like. It's going to be a curve. Let's see what it's going to look like. Notice the values for the range, go as low as negative 1 and as high as positive 1. We learned about that before. So let's mark off one. Let's put 1 right here. And let's put negative 1 right here. That way we have tick marks to show us where 1/2 is and so forth. Alright, so we had 0, 0, which is going to be there, but then we need some other values in here. We're gonna go ahead and plot 1, 2, 3, 4, 5, 6, 11, 12. Let's see how many we got here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, perfect. This will be enough. Okay, so pi over, this one will be pi over 6. This one will be pi over 3. This one will be pi over 2. They're actually very equally spaced apart. Pi over 6, 2 pi over 6, 3 pi over 6. 4 pi over 6 is the same thing as 2 pi over 3. 5 pi over 6. 6 pi over 6 is pi. 7 pi over 6. 8 pi over 6 is 4 pi over 3. 9 pi over 6 is 3 pi over 2. 10 pi over 6 is 5 pi over 3. 11 pi over 6. And then 12 pi over 6 is 2 pi. Okay, so at pi over 6 we had a input of pi over 6 and output of 1/2. At pi over 3 it was at 0.8. It was pretty close to 1, but not. It was past 3/4, just a little bit past 3/4, not quite to 1. Pi over 2 was 1, and that's where it peaks. That's a maximum value right there. At pi over 2, the maximum value is 1. But then it starts falling. At 2 pi over 3, we're at that 0.8 or 87 or whatever it was. 5 pi over 6, we're at 1/2. And then at pi, we're back to 0. And then it dips down below the x-axis. 7 pi over 6, we're at negative 1/2. 4 pi over 3, we're at negative 0.867 roughly. 3 pi over 2, we're at negative 1. At 5 pi over 3, we're starting to climb again. 11 pi over 6, negative 1/2. 2 pi, 0. And you could find more values in between these, and what you're going to find is that if you found every single ordered pair possible in between those, you end up with this nice smooth curve. The sine curve is very smooth, and it's often referred to as the sine wave. If you look at it closely, you can see why. But there you go. There, it keeps repeating in the pattern. If you go to the left, it's going to keep repeating that wave-like pattern. So if you go over, it'll come down here, and then when you go over, and it'll come up to here. It'll keep going like that, and over here it'll also keep going. It'll come up and then start going back down. It just repeats infinitely. It just keeps the maximum value being 1, minimum value being negative 1. And it'll just keep going. Nice sine wave. It's very symmetric, very pretty. Okay, if you look closely at it, you've got your domain. It keeps going, so your domain is negative infinity to infinity. And then your range goes from negative 1 to 1 inclusive. The period, in other words, how often it starts repeating, is 2 pi. You pick any point on this wave, and you go from that point 2 pi, and you will see where it starts repeating itself again. So every 2 pi it repeats. As far as looking at the symmetry I mentioned earlier briefly, it has origin symmetry. If you rotated this piece here around the origin, you would line up with this piece here. Or if you took the entire right side and rotated around the origin, you'd end up matching up with the entire left side. So it has origin symmetry, and it's an odd function. It is a function. It passes the vertical line test. Each input has one output. But odd function. The sine of negative x equals negative sine x. So in other words, over here, these x values are negative. The sines of those are opposites of what the sine values were for the positives. Like pi, if sine of pi over 6 is 1/2, then sine of negative pi over 6 is negative 1/2. So it has origin symmetry, being an odd function. There you go. There's a little bit about it. Okay, now we're going to go further than this. It's not enough just to graph y equals sine x. We're going to go further, of course, but I wanted to first just introduce the graph to you. Okay. Now, we're going to, ultimately you can do all kinds of things to the sine graph that you could also do to other graphs. Like back in college algebra you learned about taking quadratic functions, the graphs were parabolas, and doing things like shifting and reflecting and stretching and so forth, stretching and shrinking. But you can do that with sine graphs too. Let's just start with like one thing at a time. Let's take the y equals sine x function, and let's say we multiply the sine x by some value, and we'll just call it a for now. Now we learned in algebra that if you multiply by some value out front, this can cause a vertical stretch or shrink of the graph. Multiplying by a, if absolute value of a is greater than 1, that's going to cause a vertical stretch. If absolute value of a is less than 1, then that's going to be a vertical shrink. So in other words, if it's a proper fraction, if a is a proper fraction of some kind. So then, in that case, you got the stretch or shrink, the period will stay the same. So, for now, it'll still be a 2 pi period, but stretching or shrinking the sine, like the sine already looks like this, you start stretching or shrinking it. Let's say you stretch it, then you're affecting something called the amplitude. The amplitude tells us the value, like the distance of the maximum or the minimum point from a horizontal line that cuts through the center of the graph, of the wave. So whenever it's a distance, so it's absolute value of that a, tells us our amplitude. Like wherever your graph is situated, if you drew a nice horizontal line here that goes through and cuts it perfectly in half, then the amplitude tells you how far your maximum is from that line or how far your minimum is from that line. So whatever you're multiplying by, this a here, whatever that number is, that's going to be that value for you. Okay, for instance, let's say you have y equals 3 sine x. Okay. Let's look at ordered pairs. Okay, let's say you use 0. Okay, sine of 0 is 0, 3 times 0 is 0, so that doesn't change. But let's say you use pi over 2 next. Well, normally the sine of pi over 2 is 1. But now you're taking 1 times 3 and getting 3. So there you're going to see the vertical stretch. The maximum point goes up higher this time. Let's say you do pi. Sine of pi is 0. 0 times 3 is 0. And then let's say you do 3 pi over 2. Well, sine of 3 pi over 2 is negative 1, but negative 1 times 3 is going to give you negative 3. And then 2 pi, sine of 2 pi is 0, 0 times 3 is 0. So right here you can start seeing what's happening with this amplitude. Okay, let's graph that. Alright, let's say you have, let's mark it off here. Let's see if we do, can we do 4? I have enough space to do 4. Yes, it's going to be at the very top here. Okay, so this is 1, 2, 3. 1, 2, 3, 4. This is going to be negative 1, negative 2, and then down here will be negative 3. Alright, and we used 0, then we got pi over 2, then pi, 3 pi over 2, and 2 pi. Alright, 0, 0, That didn't change. But then at pi over 2, instead of 1, we have a 3. That's up here. Then at pi, we have a 0 again. And at 3 pi over 2, instead of a negative 1, we have a negative 3. And then at 2 pi, we have a 0 again. It's still cyclic. It's still a sine function. And there's still values in between here we could have filled out, but you know, for the sake of this, I just wanted to do one period. So I knew the period was 2 pi. So using 0 and 2 pi gives me the beginning and end. Using halfway between pi gives me another of the x-intercepts. Halfway between 0 and pi is pi over 2. That's where my maximum occurs. Halfway between pi and 2 pi is 3 pi over 2. That's where my minimum occurs. And honestly, that's all I really need. X-intercepts, maximum, and minimum to get a sketch of one period of this. And since it's cyclic, I could continue the sketch as needed. Tricky part is drawing the curve using my pen here. Just forgive me, it's not going to be very pretty. On paper and pencil, I'm much better at this, but trying to draw it on this bamboo tablet's a bit of a tricky endeavor. Alright, coming down. And then coming back up. Again, my curve is not being drawn perfectly, but you're going to get the idea at least. But you can look at it now, that sketch, and you can see the difference. You know, the original graph looks something like this. I can get it to draw it. So you can see the x-intercepts are the same, the period's the same. It still goes from 0 to 2 pi, but it's been vertically stretched because we multiplied by a number of 3. The absolute value of 3 is greater than 1, and that caused a vertical stretch by a multiple of 3 there. Now if you had used a fraction, like a 1/2 or something, then you would have had a vertical shrink. Okay, so that's an example of what's going on with amplitude. Okay, for our next example, let's talk about what happens to the period if you take your x and multiply by some value. Okay, absolute value of a is still amplitude, so knowing that's helpful. Now the period of sine x is 0 to 2 pi. Like for one period, you can go from 0 to 2 pi, and then you can repeat. So, but when you're doing the sine values, and you're doing sine of, you're doing the sine of 0, the sine of pi over 2, you know, so that bx has to fall somewhere from 0 to 2 pi, like if we're doing one period of this, because you're doing sine of all these values in between from 0 to 2 pi. But what we can do is set up an inequality here and say, well, if bx, if you're taking the sine of all these values from 0 to 2 pi, and bx is what is equal to something in there, we can set up this inequality to see just what the relationship is with b. Let's divide everything through by b. Solve this inequality for x. And we start to see how the period gets adjusted when you do multiply by b here. We learned about this in college algebra, about graphs being horizontally shrunk or stretched. If the b is bigger than 1, what happens is you get a horizontal shrink. By a factor of 1 over b. If b b is between 0 and 1, you get a horizontal stretch. By a factor of 1 over b. Okay, the next one's graph. All right. So let's say we have something like y equals 2 sine of 1/2 x. And we were going to graph that over, let's graph it over 0. Let's see what kind of window we want to give it. Let's try 0 to 4 pi. Let's do that. Alright, so on this one, the amplitude is absolute value of 2, or 2. Because that's the number in front of sine 1/2 x. To do the period, even though you're doing sine of 1/2 x, 1/2 x is going to fall from 0 to 2 pi. So you got 0 is less than or equal to 1/2 x, which is less than or equal to 2 pi. Multiply everything through by 2. 0 is less than or equal to x, which is less than or equal to 4 pi. So now, instead of your curve starting at 0 and ending at 2 pi, your curve's going to start at 0 and end at 4 pi. It's going to be a horizontal stretch. Because the b is 1/2, it's between 0 and 1. So you end up with a horizontal stretch by a factor of 1 over b. 1 over 1/2 is 2. So a factor of 2. In other words, whatever you had before horizontally, you multiply by 2, and now that's what you have horizontally for your period. So if you do a quick little xy table, if x is 0, y is still going to be 0. If x is pi, y will be 2. If x is 2 pi, y will be 0. If x is 3 pi, y will be -2. And if x is 4 pi, y will be 0. Okay, let's take a look at that by a graph. Okay, so let's say we got 1, 2, 3, and here's 1. And 1, 2, 3, here's 2. Then 1, 2, 3, here's -1. 1, 2, 3, here's -2. Because our amplitude being 2, we need to go up to 2 and down to 2. But if we mark that off, let's put pi here, 2 pi here, 3 pi here, and 4 pi here. Okay, so for our values we had, what, 0, 0, pi was 2, 2 pi was 0, 3 pi was -2, 4 pi was 0. So this graph ends up looking like this. Okay, so quite a difference. If we think about what just y equals sine x should have looked like, y equals sine x would have ended up being like this. Let me undo that. I'm having a hard time sketching it good here. Let's see. Halfway point's about right there. Okay. Trying to see the points to do this. The halfway point would be about right there. Okay, so normally the graph would have looked, the black one's like y equals sine x. Now since we have an amplitude of 2, this graph is twice as high here and twice as low here, so it's been vertically stretched by that factor of 2. But then also, since we have sine of 1/2 x, it's been horizontally stretched by a factor of 1 over 1/2, or 2. So instead of going from 0 to 2 pi, it goes from 0 to 4 pi. And then it repeats, just like any other sine graphs that we've been doing. Okay, so that's a little bit about introduction with the sines. Want to briefly talk about cosine as well, introduce those. We're not going to do, in this podcast, that's as much as we're going to do for now. The next podcast we'll get into starting to do all kinds of shifting and stuff, but just want to introduce the basic functions to you right now. Now y equals cosine x. If we go back to our unit circle, the cosine was in the x values here. Notice the cosine started with 1. Went square root of 3 over 2, square root of 2 over 2, 1/2, down to 0. Then went down to -1. Then came back up to 0, then came back up to 1. Cosine, just like sine, is cyclic. And you end up seeing a lot of the same, end up seeing the same values in the domain and range, just not paired together the same way as you have with sine. Like if you start looking at y equals cosine x, at 0, cosine of 0 is 1. And then at pi over 6, you get that crazy, how before, like at pi over 3, we had the 0.87. Well, cosine is different. At pi over 6, you got the 0.87. Then at pi over 3, you've got the 1/2. Then at pi over 2, you've got 0. Then at 2 pi over 3, you got -1/2. Then at 5 pi over 6, you got -0.87. Then at pi, you got -1. And then it starts climbing again. 7 pi over 6, you got the -0.87. At 4 pi over 3, you got the -1/2. And then 3 pi over 2, you're at 0. And then it's climbing back up. Got 5 pi over 3, that's 1/2. 11 pi over 6, it's 0.87. And at 2 pi, it's back to 1. And then it repeats. It's cyclic. It's just like sine was. So let's mark this off and look at some of those values. We'll put 1 right here. Put -1 right here. Okay, pi over 2 is right there. Pi. 4 pi. 3 pi over 2. And 2 pi. Okay, so at 0, cosine is 1. At pi over 2, cosine is 0. At pi, cosine is -1. At 3 pi over 2, cosine is 0. At 2 pi, cosine is 1. And if you want to, you can fill in some of those in-between values. You got like the 0.87, you got the 1/2, you got the -1/2, the -0.87, the -0.87, the -1/2, and you got the 1/2, and you got the 0.87. So that gives you, some values there. I've only been using this bamboo tablet thing for like 5 or 6 years, but maybe in another 5 or 6 years I'll have it mastered and be really good at drawing on it. But anyways, there's the cosine. Gives you an idea. It just like the sine, you've got the domain is negative infinity to infinity. The range takes you from -1 to 1 inclusive. You got period of 2 pi. This one, though, turns out to be an even function. Has y-axis symmetry. If you look closely at it, if it repeats, as it repeats over here, you can fold the paper or fold the graph along the y-axis, and the left side is going to match up with the right side. And with that y-axis symmetry, it's also an even function. If you take cosine of a negative x, it's going to equal the same thing as cosine of x. So like if you have cosine of negative pi over 2, or yeah, cosine of negative pi over 2, that's going to equal the same thing as cosine pi over 2. If you have cosine of pi over 3 is 1/2, cosine of negative pi over 3 is also 1/2. Doesn't matter whether you're doing the cosine of a positive or a negative, you're going to end up with the same output. And I keep referring to the fact that this has a lot of similarities to the sine graph. In fact, if you really look at it closely, this is the same as the sine graph with the phase shift, a shift of pi over 2. Like if I went ahead and superimposed the sine graph on here, for kicks and greens, let's put the sine on here. You see that? It matches. But it looks like one of them's one step off from the other. In fact, if you look closely at any 2 points, there's a pi over 2 difference. Y equals cosine x is y equals sine x with a phase shift of negative pi over 2. In other words, you take y equals sine x and take it negative pi over 2, so take it to the left, pi over 2, and then that matches up with y equals cosine x. Pretty cool, isn't it? So cosine x equals sine of x plus pi over 2. And we'll get more into the phase shifts and stuff like shifting later, but just wanted to kind of just point that out. So we say that these are sinusoidal graphs. Sinusoidal functions. Okay, and just like sine has the amplitude and the period and all that work you do with it, cosine does as well. So let's look at graphing a cosine that has some fun stuff going on with it. Let's say we have something like y equals -4 cosine pi x. Let's do that. Okay, the absolute value of -4 is 4. That's our amplitude. Now since this cosine graph is going to be situated above below the x-axis, 4 gives you how many units above the x-axis to find your maximum and how many units below the x-axis to find your minimum. And then for the period is 2 pi, just like with sine. So when you're doing the cosine of 0, cosine of pi over 2, cosine of pi, cosine of 2 pi, after you get past 2 pi, it starts repeating. So that pi x has to fall, like if you want to do one period, that pi x has to fall from 0 to 2 pi. Divide through by pi, and you get 0 is less than or equal to x, which is less than or equal to 2. So 2 is the period. Alright, so if we want to go to graph this, we could do a little xy table here. I'm doing it all, and then we'll still graph on this grid too. Like if you have x is 0, well, cosine of 0 is actually 1, and 1 times negative 4 is negative 4. If you have 1/2, cosine of pi times 1/2, cosine of pi over 2, which is 0, times negative 4 is 0. If you use 1, cosine of pi times 1, cosine of pi is going to give you negative 1, times negative 4 is going to give you positive 4. If you use 3/2, cosine of 3/2 pi is going to give you 0, times negative 4 is going to give you 0. And if you use 2, cosine of 2 pi is going to give you 1, times negative 4 gives you negative 4. Let's see, let's mark off 1, 2, because that's our x values. And then let's see here, I got 1, 2, 3, 4. How many of these do I have? Alright, let's do 1, 2, 3, 4, and do negative 1, negative 2, negative 3, negative 4. Okay, so 0, negative 4, 1/2 comma 0, 1 comma 4, 3/2 or 1.5 comma 0, 2 comma negative 4. Alright, so we have several things going on here. Of course, when you connect your dots, make it a little smoother curve than that. But we have a stretch for sure because of that 4. It's really high up there, really low down here. But it's a negative 4 out front, so what that ends up doing is reflecting across the x-axis. Where originally this would have been, if it was been a positive 4, it would have been up here, and down here, and up here. But since we're dealing with a negative 4, it reflects across the x-axis. So it's almost like it's upside down or something. And then the period of 2, so it goes from 0 to 2, and then going to the left you start over, going to the right you start over. But there it is. So there's your cosine. Okay, just real quick too, I just wanted to put some of these in the calculator so we can have a little fun looking at that. You can put these in your calculator. Make sure that you're in radian mode, because that's what this is all about. But you can go to y equals, and like earlier we had done y equals sine x, you can type sine, and then hit the xt theta in button, and then hit graph. And I really don't like that window, it's not really giving me a good view. You can always go to the window button and change your coordinates, or you can go to like zoom. Number 7 says Z trig. Let's try that one, see what it does. Well, that's nice. That it made it prettier. It's easier to see what's going on. And then, later we also did y equals, what was y equals 3 sine x? So we can go down and we can graph 3 sine x at the same time. You might look at that and go, well, that's cool, but I might forget which one's which. So if you want, you can scroll down on y2 and scroll over, hit enter to make the line thicker for the y2. If you hit enter again, it'll give you other options, and if you go, oh no, I went past what I wanted, just keep going, it'll start over. So there's the line, thick line, and so when you graph it again, y equals sine x is the thin one, thin curve, and then y equals 3 sine x is the thick curve. You can compare that way. You can also go to the table. Second graph takes you to the table, and you can see some ordered pairs for x and y for both y equals sine x and y equals 3 sine x, so forth. Yeah, that kind of stuff. Or just now when we were doing the cosine graphs, we just did that cosine x. Let me see. Let me clear this and start fresh. Clear. All right, let's do cosine x for the first one there. And then we had just done that other cosine graph. I just lost track of it. There we go. Negative 4 cosine pi x. You can type negative 4 cosine pi x. And then let's go ahead and make that one thicker, just because it's fun to do that. And then hit graph. Isn't that cool? You can definitely see the difference there. You can not only see the amplitude, what the 4 did to it, but like for the regular cosine x, you have a maximum here, but with negative 4 cosine x, you get that reflection, and so it's a minimum here. And where and then it's that you've got that horizontal. It's vertically stretched, but you've also got this kind of a horizontal smoosh. So you can quickly compare the two and see what's going on. So the calculator can be a great tool with the graphing. On your test, you'll have to be able to graph by hand, but the calculator can be very helpful for word problems and other situations. Okay. Well, thank you for joining us on the sine and cosine graphs. Tune in again to learn more about these, especially with getting into shifting them all over the place. That gets really fun. So I look forward to seeing you again soon.